whenever you run the machine learning with the R in the interface, you just run that algorithm, only change the K or the training set. And now, the other concept is a confusion matrix. Some people are yawning. It seems that you are getting really bored, huh? We're going to end it soon. Look at that confusion matrix. Have you heard of that concept before? Yeah? Confusion matrix, it means that how great your algorithm is able to predict based on your training set. The confu mat is a function with the R. It's a function with the R. It's always there. You only simply put the name of the algorithm inside. And it measures the accuracy. I'm just going to run it. You see a table at the console. At the console, you see a table. At the diagonal, you see 13 and 16 for BCR, ABL, and for the name. And at the off diagonal, you see 2 and 4. What does it mean? It means that your machine learning, but before that, can someone tell me what is the purpose of writing a machine learning algorithm? The higher goal, the ultimate goal of writing machine learning. Anyone? Any guess?
Make predictions.
Make predictions. That's right. Why you are here? To learn an algorithm to make prediction. Okay? And that's it. It means that the machine learning with confusion matrix made 13 plus 16 correct prediction. But it just made 2 plus 4, 6 incorrect prediction. So this is not bad. It can be improved. We show that later. We can just make it more accurate to have 0 prediction, but that's so far what it is. And now, sometimes you come to ask yourself, I don't like to see the matrix, the table. It's not, I should say, it doesn't tell me anything. It means that 13 plus 16 is 29 correct prediction, 6 incorrect prediction. What does it mean? You come to measure the rate, error rate. I call that error rate KNN. That's a formula. You can always run that like that, and it gives me, what is the rate? 17% per 14. It's the error rate. It's not that bad. Only 17% is a chance that you just make a wrong prediction. Then if our purpose was that, to be either magicians to make prediction, you didn't do a bad job. It's good. 17% error rate. It can be improved, but it's still not bad. We met our first goal. Make predictions on cancer genomics. Then you were able, on your training set, to show the type of the cancer by prediction. But you just go 17% the chance that go wrong. It can be improved, but our purpose is fulfilled. You made a good prediction. Yes, question? No? Wasn't that fun? Yeah? Okay. What time is it? We have almost 20 minutes. I hope that they finish it within 20 minutes. We are just going to run, I should say, I was planning to just cover 3 algorithms for machine learning. You can keep working on those algorithms forever. There is a lot of things to learn. It's a kind of a taster to see if you like the taste or not. It's like, for example, tasting something. If you don't like it, put it aside. If you like it, just buy it more and try it more. Okay, the second algorithm, this is called linear discriminant analysis. For the linear discriminant analysis, you have to use a Bayesian statistics. I'm sure that you think, oh, what an interesting math formula is there. Wow, I like it. I'm sure everyone likes this math formula. That's a Bayesian statistics. If you don't like it, no worries. We do not go there in the next 20 minutes because it takes so much time. I don't know why I think that 2 hours is enough for every stuff. I was wrong. But anyhow, but for the linear, I should say, discriminant analysis, it makes some prediction based on probability. That's all we know. And sometimes it makes good predictions. That's one of the few, I should say, machine learning algorithms. To run that algorithm, it's very easy. When you run it in the R, you do not need to just go to read many books. You just go to the ML interfaces. You just go to use the function mlearn for machine learning. You know what is the formula? It's going to be your prediction. Your prediction is that thing, the type of the cancer. Tilde dot. It means that the type of the cancer can be the function of anything in my data sets. You employ thousands of variables there. Dot, the data is your data set which you created from your cancer. You know how to prepare that thing so far. You just learned before the break. And the method, look at that, diagonal linear discriminant analysis I. It's always easy. You do not have to do anything. That's a package is already written there. Only you add one I there because you are in the interface you run. And the train IND, it's a training set that you prepare. Then essentially, by this formula in R, with the machine learning interface, you only have to prepare your training data sets, which we did it before the break. Then any type of the cancer which you have, simply use that template, only put your training data set there. The algorithm is written there. The linear discriminant analysis is there, only you just type it there. I'm just going to run it. I call that DLDA1. And this is run. The second thing, you come, okay, let's see the prediction. As a machine learning expert, your job is always to make a prediction. And when you make a prediction, you have to assess if you were right or wrong. And you do that always, remember, with the confusion matrix. You do not have to write anything except to just write that formula, confumat. It's a package already written to assess the accuracy of your machine learning. Then you just go there, only type the name of the functions which you had, control info. Wow, I'm impressed. It seems that we made a better prediction. Now we have on the data, the diagonal means the correct prediction, 13 plus 17, your algorithm made correct prediction. But 2 plus 3, the algorithm made a mistake. But how much is the accuracy which you have made? Previously you had 17%. I'm very impressed. Isn't that nice? The error rate which you made with linear discriminant analysis is now 14%. With the KNN, you had 17%. With a different algorithm, you had it improved. So far, it seems to me, without making any improvements, linear discriminant analysis does a better job. Don't you agree on that? There are some techniques to improve it even further, but I'm afraid that you have no time to do that. But still assured that you can reduce it to 5% to make the accurate prediction. So far, so good? You feel happy now? You learned 2 algorithms for machine learning for cancer genomics, linear discriminant analysis, and KNN. Aren't you happy now? Just only learn as a template, just prepare your data sets, run the algorithm. Okay. Now, I have to just run through that very quickly. One of the purposes, are you okay if you stay 5 minutes more? Everyone's okay to stay 5 minutes more? Because one of the purposes to run, I should say, the workshop was to tell you, when you just work with the cancer genomics, you have a lot of features, and those features is running you crazy. You just want to get rid of them. With the microarray experiments, when you have sometimes hundreds of thousands of the features, not all of them is useful. Huh? You don't need them. You have to identify those features that you do not like them, it's going to be not useful, to set them aside, pick up the ones which is helpful for your analysis, and run your experiment with them. Why this is important? Because by doing so, you can improve your accuracy of the prediction. If you got to 14%, if you do, they call that gene selection or feature selection. If you do that, very simply, you have better data sets and you can increase the efficiency of your algorithm. That's the purpose for it. Huh? And that's the thing which I want to do. It was actually one of the main goals for this, I should say, for this workshop. To tell you how to reduce, get rid of some genes, some features, and improve your prediction. Okay? We have two algorithms for it. If you like statistics, like me, and I hope you like it a lot, you can just use, I should say, this function as a t-statistics to pick up the genes which they give you the least p-value. When the genes give you the least p-value in t-statistics, it means that they are the genes which you should fall in love with them. They are the key for your analysis. And in order to do that, you can always use this code as a template. You just run t-test. It's a function comes with the gene selection, with the gene filter. You run it, you order it, you see the order function, and I put decreasing true. It means that you order the t values from the least to the highest. Then it means that you pick up the, and you just select the feature names. It's a function which simply selects those functions. Sorry, I do not explain about them too much. You are short in time, but feel free to email me or just contact me if you need some clarification on that thing. We can just explain that more, or simply do your search on the literature of the t-test for feature selections for cancer genomics. And now, look at that. What did we do? On the training selector, everyone has that code, huh? For gene selector. Now, you have only 50 genes. Look at the last line, train selected on the t-statistics. Do you see it here? 1 to 50. I highlighted there. It means that I only selected out of thousands of features, only the first 50 genes. Then I got rid of the curse of dimensionality. And what to do now, I'm just going to repeat my algorithm for K and N, K nearest neighbors, but on a different data sets. I have K and N and 2, I call that the second algorithm, mlearn function. You should, from tonight, you have to love that function because it does all the job for you for machine learning. The formula is there, nothing changes. The data sets, you only made a minor change that you put in slicing the data only to the training selected. You only put 50 genes there. And the method still KNNI with the first nearest neighbor. When you got back home, as a practice, you can change K to 2. You can change K to 3 to find how the error rate changes, because it changes when you change the K. And the training set is where it is. I'm just going to run that function. Let me just do that with 40. For me, it's out of range because I just selected only, I should say, 99% of the cutoff rate. Maybe you can do a better job. Can you run that function? Okay, it just ran for me. I'm just going to run the confusion matrix. Now look at that. And I have the error rate. Let's see how much the error rate is that. Originally, wow, what a feat. For the KNN first, when you run it, without gene selection, you had, if you remember, you had the error rate 17%. And now, when you rank the gene, you selected your features, your error rate is now 14%. It makes big, I should say, difference. Still, there are some more room to improve. When you change K, you see that even you can reduce that 14%. And also, we do the second thing. We use the same data sets as a feature selected to run the linear discriminant analysis, which we already got 14%, I should say, accuracy, the error rates. I'm just going to run the confusion matrix. Let's see if from 14%, we have a better chance to reduce it. Oh, it didn't just work that much well for the linear discriminant analysis. Then the gene selection, it worked much better on the K nearest neighbors than, let's say, on the linear discriminant analysis. That's why the job of a machine learning practitioner is so much fun, because you have to play around, try different things, and analyze them and make the best judgments. Any questions so far?
Are you running confusion matrix on the test set or the training set?
We run on the test set, then we just go to the random forest. Okay, and now, that's going to answer your question on the test set. Okay, I feel a little thirsty. Okay, and now, it is going to be one of the interesting part in the machine learning practices, and that's cross-validation. Who has heard that terminology before? Cross-validation. What do we mean cross-validation? It means that you just run, I should say, your algorithm on the test set. And sometimes you have different approaches. You just divide, for example, they call that k-fold. You divide your training sets on 10 partitions, and for each one you run the test set and you run the confusion matrix and you just sum them up. But the measure which we're going to do here, it's because when you just work with the R and with the machine learning, I should say, interface, it's done for you. How is that done for you? If you just come over there, you define a different algorithm there. Define a different argument. X-val spec means that cross-validation specification. Simply, sorry, I had to just go one code about. You just put, I should say, the type of, I should say, the cross-validation. I put LOO. It means leave one out. If you just go to the help menu, it shows you different algorithms. Leave one out means what? Every time, for example, you said talk about the test set. You run your machine learning algorithm, you exclude one data from it, run your algorithm, and test your accuracy on the thing which is left behind. And you aggregate them at the end. And that's what it means. I'm just going to run it, and I'm just going to run a confusion matrix, and I see that the confusion matrix is not a little different, but it means that 27 plus 34 correct answers, 10 plus 8 wrong answers. The cross-validation in the whole data sets give you a little, I should say, tricky, I should say, prediction. You have not a good, I should say, accuracy. Okay, and now you have 10 minutes, huh? Also, when you do cross-validation, you leave one out. When you just work on the cancer genomics, you're always interested to also select the features which has more relevance to your analysis. Feature selections. Previously, I did that with t-statistics. You remember those 3 line of codes? You may not like those kind of codes because it's not easy to just run the t-test on each row, then order it, then use the feature names. If you don't like it, no worries. You come here with the x-value specification. There is a function, this is called fs1, equals fs abs t. And I just put a number there. That number does exactly the same thing as we did with the t-test, but here this is automated. It just extracts, for example, the 50 most relevant genes from your, I should say, data sets. You do not have to just do the statistical analysis. The t-test, it's already there with that function. You need, for example, 20 top genes which contribute to the cancer. You have no idea which genes are more relevant, have causal effects for the cancer of the leukemia. That's what we are doing. You just choose 20, and the algorithm for machine learning, while does the cross-validation, finds the most relevant genes which causes the type of the cancer which you are looking for. And I'm just going to run it. I'm just going to do the confusion matrix, but I'm more interested in the third option. Table, unlist, fs history, knf4. That function, fs history, it's going to give you the name of the genes which you selected. You were looking for the top 20 genes, has a causal effect. For the leukemia cancer, with the fs history, it gives you the name. And later, we see the symbols of these genes. No need for the t-test. When you just prepare your data set so well, then you can copy-paste the algorithm to find, I should say, the genes which causes the cancer. Okay. And now, let's skip a little. we just go to the last algorithm. We have 7 minutes for the last one. I like that algorithm a lot because it's a very powerful algorithm which is called random forest. I like the name, random forest algorithm for machine learning. Huh? How it works? I just made it very simple, I should say, stuff over there. It's a simple, I should say, demonstration of a tree when it comes to making decision. Look at that, it's a very simple one in order to conceptualize the concepts. You start with a big question. For example, am I hungry? Either your answer is yes or your answer is no. Depending on your answer, you just make another one. How about $25? I have it, I go to a restaurant, I don't have it, I just buy a burger. I got it from the Wikipedia, but that's the essence of, I should say, a tree, a decision tree. But when you have lots of trees, let's say thousands of trees together, it becomes random forest. And they have a very high power to make accurate prediction. Okay? And now, you're just going to do the same thing. Don't bother yourself to write the codes. You just go to the machine learning interface in the R. You just write mlearn function, the same thing, the formula, tilde dot, the data. But for the method random forest, But before that, you have to install the package for random forest. It's going to be install.packages, random forest. Remember, R is small, F is capital. And it comes with the R, not with the bioconductor. Then installation is much easier. Just use install.packages. And the library comes for random forest. I'm just going to install it. And this is installed. When this is installed, simply I just go to the machine learning, and you will see that I have random forest I, because I'm just working the interface, and I have training set, but I have two features which I added. This is n-tree, means the number of the trees, because you are working not with a tree, you are working in a forest, and as many trees as you will have a better prediction. I just choose 120, I should